Okay, hey guys. Tonight I want to share my perspective on what I feel design really means in engineering, and it's just an opinion, my opinion. And what are the benefits to thinking of design the way I'm going to present it to you when you are in a business of developing products to sell in the market, or if you're in a business of providing design engineering services to other companies. And when I talk about design engineering services and developing products, I'm not talking about things like artistic products because I'm not a professional artist. Although on the side as a hobby, I do read a lot of comics and I enjoy drawing cartoons. But that's something that we can talk about some other time. Um, but tonight I want to talk about technical product development, things like developing, say, some optical system, some detection system, a virus detection system, or it could be a spectroscope, a spectrograph, things like that, a laser scanning system, things like that, scientific type technical instruments in product developments. And what when we're doing design, when we're designing those instruments or we're designing an optical system, what does it really mean to design? And that's what I'm going to try to present here tonight. So what happened was every March of the year in Canada, here in Canada, I live in Vancouver, Canada, in British Columbia. Every March is National Engineering Month. And on March 9th of this year, I created a bunch of slides, which is having this title slide that you see here, and I posted it on LinkedIn. So tonight, I want to kind of orally articulate for you what I was trying to convey across and maybe add some further perspective to it. All right. So what is design in engineering, or what do I mean by design in engineering? Right. Okay. So let's say that someone asks you, and you're an engineer, a design engineer. Someone asks you to design a an inclined plane, right, with some angle theta that lets a block slide down, and the plane is frictionless. Let's assume that it's a frictionless plane. Um, and it must achieve a certain velocity v, 100 miles an hour, 200 miles per hour, some kind of speed, some velocity, right, on a frictionless plane. How would you design that plane? Right? How would you do it? Would you would you build 20 inclined planes at each at different angles and try sliding a block down and measure the velocity and pick the one that suits that velocity that your customer asks for? What would you do, right? So here's an example of doing that, like trying different planes at different angles. That's trial and error, okay? So you could do it by trial and trial and error is not a bad thing, but depending on what the problem is. But in my perspective, to my perspective, to design something is something more deterministic than that. And when I say deterministic, I don't mean exact. Right? We'll talk about that later on. What I mean by deterministic, but um, what I mean is there's an element of prediction or predictability when you design something. To design something means you got to be able to predict something about it. Okay? And I will elaborate further what I mean in terms of optical system design. Right? So so how would you design the inclined plane if to make it more deterministic? Well, you would apply known laws from physics or from mechanics. If you're a mechanical engineer, you can apply laws in mechanics, which traces back to physics anyway, right? So you might sketch a block diagram like this with height h and a block frictionless plane velocity v, and you can apply Newton's law or you can apply shortcut, which is the conservation of energy. Because in this case, if you got a frictionless surface, then you can just conserve energy. And you can write on one side of the equation mass times gravity times height, which is your potential energy. I say that and cringe a little bit because I know that physicists look at that like real physicists. Like I'm sort of a physicist. 'Cause I did undergraduate degree in physics and in optics, but um, real hardcore physicists will look at that and go, "Oh, are you sure you know what you're talking about with potential energy? Because potential energy, there's no such thing, and so on and so forth." There are discussions about the idea that there's no such thing as potential energy. Just look it up. Not on Wikipedia. That's not a trustable site. Look it up in the European Journal of Physics and some other textbooks, and you'll find a discussion. Anyway, um, it's for our purposes, we can write potential energy on the left side and kinetic energy on the right side. Because the idea is if you put a block up on an inclined plane, it has a certain potential energy, and then at the bottom of the plane, it has a certain kinetic energy, and they're equal because one is converted into another. If you write out the equation like this, you find that the masses cancel, and if you solve for velocity, you get, okay, I think I'm blocking the view here, velocity, okay, solve for the velocity, you get this equation, square root of 2 times the gravitational acceleration times the height of the block. All right, and what's the value of doing that? The value of doing that is now you know that it's independent of angle, right? It's independent of angles. That means you don't have to spend a lot of time and effort building 20, 30, 50 prototype inclined planes. Try them all out because it does not depend on the angle. It depends only on the height. You can have any angle as long as you start at the same height. They all reach the same final velocity v at the bottom. And that is the power of applying your knowledge of known laws of mechanics or physics or whatever you trained on in designing this inclined plane, right? And then you can go back to your customer and you can say, uh, by the way, it doesn't depend on angle, okay? And I can prove that to you either by way of a simulation or by way of building you, let's say, one or two prototypes, each with different angle to prove to you that actually it doesn't depend on angle. Or you can just trust me as an engineer, right? Okay, and you can write out your equation this way. You always get the same velocity. If you change your angle, you just change the sliding distance d because they are related by the sine of the angle. It's just trigonometry, right? And now you're applying mathematics, right? Okay, so this is kind of what I mean by design in engineering, is that there's some kind of element of predictability within tolerances and uncertainties, right, to it. And uh I will try to elaborate what I mean by that in optics. Okay, so all right, so like in optical engineering, here I'm saying that the design of optical systems involves applying known laws into powerful computer programs like the ZMAX optical design program or the Light Tools or Trace Pro or Code 5 or there's so many programs. So Oslo, for example, they're all very, very excellent programs to predict results. We have to predict stuff like image quality, MTF, modulation transfer function, image distortion, illumination uniformity. All these things are meant to be as predictable as we can within tolerances and within uncertainties because they have to be measured. Okay, so that gets us to optical system design now, which I'm gonna before I do that, let's see. Oh, I also say in this slide that good designers should strive to be good experimentalists. Obviously, you should test what you design, right? And so that's the portion of optical system design or design in optical engineering where you've got to test what you design, right? Um, and then I have my last slide here in celebration of Canada's National Engineering Month. Okay, so now let's go back to this point about applying known laws into powerful programs in optical system design. Um, okay, so if you are a lens designer, um, you would know that very often, if you are in a design services company working as a lens designer, almost every month or every other month, you'll be receiving a table of specifications from the business development manager or your manager, where a customer has asked for you to design a lens that has to meet these specs. And they're very exact. They're saying MTF has to be greater than 80% at this spatial frequency. They say, I want image distortion to be greater than or less than negative 5% barrel distortion. And they'll specify every single thing in very precise terms. Usually it's a one-sided spec because you can't, nobody asks, no, well, sometimes, unless there are applications where your customer specifically wants a specific type of distortion, like barrel distortion, and that can happen. That can happen. There can be cases where you are in one particular experience I had. Um, I was designing an X-ray. imager, but not I'm not refracting X-rays. The imager will convert X-rays into visible rays using a phosphor screen. So X-rays hit the phosphor screen, convert to visible radiation, and visible radiation will hit a well, it will it will hit a digital. It will hit a phosphor. Okay, the phosphor screen will convert the electrons into photons, and then and a digital lens, a lens will project the image from the phosphor screen onto a image sensor, right? And there was pincushion distortion uh, on the phosphor screen. So the lens has to have a specific value for for barrel distortion, negative distortion, plus or minus a certain uncertainty, a certain variance to it. So that can happen as well, so that the barrel distortion can offset the pincushion distortion. But anyway, the point is that the specifications table are very, very precise. They want you to meet those things. So that means that you have to be able to predict that your lens can meet those specs. And these optical design programs are so powerful, they can make those kinds of predictions by way of numerical computation, right? Plus, obviously, um, tolerances. You have to do a tolerancing analysis. Okay, so um, but that's lens design. But even if you're not doing lens design, if you're doing optical system design, which is something somewhat different. Optical system design is not necessarily lens design. Optical system design is, for example, you already have an imaging lens. You didn't design it. You picked it off the shelf. But you have to integrate that with an image sensor. Not only that, you have to put in filters, beam splitters, mirrors, electronics. You have to integrate with firmware, software. If you're developing a virus detection instrument like a real-time PCR instrument, you've got to integrate your optical system with well, it's good. It's gonna have to detect light coming from fluorescence from little fluorescent molecules that are ordinarily attached to the DNA that you're trying to detect. DNA from the virus actually is RNA, but it's converted to DNA, and then and then it's amplified. That's why it's called polymerase chain reaction (PCR). Anyway, um, things can get quite complicated in optical system design. And what happens? And what happens is this: um, uh, if you are going through a project where you're developing a complicated product, usually you go through phases. So let me bring us to another screen here. Um, hopefully, I can do this right. Let's go to um, okay. So, all right. So this this is a book that I wrote, Modern Classical Optical System Design. To get to this book, you go to my website, inopticalsolutions.com, and you scroll towards books, or you can, I think you can, no, this is linked to an interview. Click on books, and you would see this book, this book, this book, this book, these books. But this book, Modern Classical Optical System Design, if you click here to preview, you will get to this page. And if you click on preview, all right, if you click on preview, you will get to see something like this. And scroll down to, okay, that's the series editor, Professor Johnson. Really, really great guy. He's kind of like he's my mentor basically in optical lens design. And he was very kind because he wrote a foreword. I have a dedication here to the optical adventurer. If you want to go on an adventure with me, read my book. The table of contents. Here's a forward that Barry Johnson wrote for me, which is very nice. But going back to the contents, you can see here I've got let's see here. Okay, forward, preface, acknowledgements. Okay, chapter 1 is imaging, and there is a first subsection on an introduction to the real world. I talk about a lot of stuff here. Click on that, and you get to chapter 1, and you see this. Okay, this is an example of what's called a phase gate flowchart. There may be other names to it, but I know it as a phase gate flowchart. If you're undergoing a very complex product development process or product commercialization process, you'll see something like this from your program managers or product managers. where you go through various stages of creating an idea, concept development, feasibility, design, design verification, and prototyping. Okay, and at each of these are phases, and each of these phases are kind of governed by phase gates. Right, you have to pass the phase. If you pass that phase, you go for you open up your phase gate, you go into the next phase. Okay, so what happens is this. Let us say that you're already in design, and after design, to go into the design verification, which is when you build your prototype, you have to spend money. And in many cases, you are facing a design review where the product managers dial into the review, and technical fellows or senior engineers are dialing in, and you've got to convince everyone that they should give you $100,000 or whatever money it is to spend on building a prototype. The question is, how would you do that? If you designed your optical system, then chances are, let's say if I was a senior engineer dialing in, helping the managers review your design and be convinced that yes, this design can go through, you can spend $100,000 to build a prototype. What would I ask? What kind of questions would I ask? I would ask, okay, what was your design rationale? How did you design your optical system? What made you decide to choose this component? What motivated you, or what was the rationale behind doing this or doing that? Did you use any equations? And most importantly, the product would have to satisfy certain requirements or specifications, right? That came from, say, the product manager. How do you know that it will meet those specifications? Now, you can't really say, when you get to that, you can't really say, well, we don't know unless you built a prototype. Yeah, but $100,000 is a lot of money. Managers will want to know, what is your confidence level that it won't be, we won't have to spend another $100,000 if the instrument that you design doesn't work. So you have to be able to provide confidence level. And the only way to do that is to be able to make some predictions, at least half the predictions, right? You can say, okay, the other half, we don't really know. We need empirical data as feedback to our design. But the another half of it, yeah, we can say that, okay, based on these equations and based on this optical simulation, we think that the image distortion will be -6% plus or minus, maybe an uncertainty of 2%. But you put in measurement error, it could be another 1%. We don't know for sure. That's fair. That's fair, right? You have to be able to make some kind of prediction and say, we think it's going to be this way. And I, as a dial-in reviewer, might ask, okay, you use this equation. Why did you use that equation, by the way? Where did you get that from? Now, don't say Wikipedia, because, oh, well, some people may be okay with it. But personally, for me, if you say you got the equation from Wikipedia, I'll say, sorry, no, can you please go back and find a proper resource for that? Because there's no traceability for Wikipedia, there's no accountability, right? Anyone can write a Wikipedia article. More so, if you say AI, eh, no, sorry, no. Okay, maybe 10 years from now, when AI has proved that it can come up with something reliable, fine, right? But as of now, I would like you, if you were, say, you're a fresh graduate or um, younger engineer, or any engineer, doesn't have, even if you're a senior engineer, even if you're a chief technology officer, and I'm reviewing your design, I would say, did you derive the equation? Can you cite a reference from a journal or textbook? And why did you cite that equation? What was the motivation for it? Right? Yeah, you can always say it's obvious. Fine, but why is it obvious? Not obvious to me. And I'm not just trying to play hardball. I sincerely would like to understand, how did you approach the problem? How did you approach the design? What was the rationale? So this is the benefit for regarding design as an action um, where you are actually making some kind of prediction. You have to be able to predict something when you design something, and not just a whole bunch of trial and error, because you will always have to go through a phase in which you are being reviewed by engineers or the board or somebody else, and you have to rationalize and justify why someone should give you money to build your prototype. You have to be able to make some level of predictions. Okay, okay. So there's this, and then the other thing about predictions is I want to talk about determinism and probability. Okay, because I keep saying you have to be able to make predictions, but it's within some uncertainty. What I mean by that is, so another book that you can go to is I have this book called Monte Carlo Simulation and Analysis in Modern Optical Tolerancing. Click on this, it'll go to the SPIE website for it. And if you click on sample pages, you should be able to see this. I think it's 4 pages long. Okay. In the introduction, I talk about what is modern about modern optical tolerancing. But more importantly, I show this example. So let's say you are designing a lens that has to possess a certain effective focal length, EFL. A simple singlet, a single element lens. It has a thickness, it has radius of curvature on the left side, it's got radius of curvature on the right side, it's got a refractive index, it's got a certain thickness, and therefore it's given by the single equation, right? Effective focal length. You can say that, okay, I predict based on a radius of curvature of this amount or that amount, thickness this amount, and index of refraction this amount, it will have a focal length of say 100 millimeter focal length, right? But it won't be exactly 100 millimeters. It's always 100 millimeters plus or minus some uncertainty or some variance because of manufacturing tolerances, but also because of maybe some measurement error or something like that. Okay, so in reality, your EFL, your effective focal length, will have a plus or minus delta variation due to any of these values here that have variability inside of it. And since each of these quantities can have some kind of distribution, can have, but usually unknown. And that's why I normally when I do tolerancing analysis, I usually do a Monte Carlo simulation, and I assume a flat distribution because it's just a fair distribution. Why should I assume that it's normal? And if I don't know anything else, I'll just assume that it's a flat square wave, distribution. All right, and so because these have distributions, and even if they're flat, it doesn't mean that the EFL distribution will be flat. It could be normal, but it may not be normal because there's something called functions of random variables. If each variable here has a stochastic nature to it, has variability, then the final parameter, which is in this case focal length, can have a distribution, right? There are ways to actually compute what the distribution is or derive what the distribution is. It's pretty tough actually to do that. But in a Monte Carlo simulation, you get the distribution right away. In optics, Zemax Optics Studio or any program, for example, if you just put in your tolerances into each variable here, you can Monte Carlo the entire focal length, and you'll get a distribution of focal lengths, and it'll look like something. Depending on what you assume for the distribution of each of these variables here. Okay, so that's what I mean by adding variability into your deterministic parameter, right? So your parameter, in this case focal length, can have a deterministic nature to it in the sense that it has an equation, but it can be stochastic in the sense that each variable can be subject to randomness when you add in tolerances in production and also uncertainties in measurement. Okay, so uh, that brings us back to, I guess, this and um, and that's it. And I hope this is clear. I hope it's clear why there is value and benefit towards thinking of design as an action that involves some level of predictability in engineering. And I hope that wish you all the best in your product development process. And that is it. Thank you. Bye bye.